Welcome back. In this part, which should be considered as a preliminary part, we will do some review of facts and some properties of Lie groups and their topological actions. So maybe I should start with the title. So let me write it down. Some facts. On Lie groups and their topological actions. So that's our title, and let's just start it. So what is a Lie group? So that's the definition. Let G be simultaneously a smooth manifold and a group with, let's say, that's a group with the multiplication and I will just write it down like M multiplication. This will go from G times G that goes to G. 10 G is called a Lie group if the multiplication M and the inverse map let's call it mu this is from G to G, defined like that. So this is in G, it will be exactly G minus 1, are both smooth. Infinity differentiable. So that's our definition. So maybe you should also emphasize that this multiplication in the group, that if I take two elements of the group, so we will basically simplify this multiplication to the notation that will be just GH. Sometimes we put a dot, sometimes we don't. So that's the notation. This is the notation. So okay, so we have the definition. So we'll give some examples. So the first example is, of course, we can take the set of all integer numbers equipped with the operation of addition. So clearly this is a group. This is a group with respect to the addition, and of course we can also consider this as a discrete set So it's like a discrete set in the real numbers, so that's definitely a manifold of dimension 0. So it's a Lie group. So this is my first example. Z is a Lie group. Of course, you can do the same thing by taking all the real numbers. All the real numbers. That's also a Lie group. And another example, and in this case, we can take, for example, the multiplicative group of real numbers, namely, we take r minus 0 and use it to be equipped with the multiplication operator. So put it multiplication operator. So of course, this is also a Lie group. So those are the, let's say, the most trivial examples of the Lie groups, and the other ones, let's start it, let's say 4, and that we have here that this can be like this, G, L, and R. So what is the G, L, and R? We have seen it already. Those are the n by n matrices. So this is A and the n matrices. So this is, let's write it down. This is from Rn to Rn such that A is linear and A minus 1 exists. So this is called, as you remember, general linear group. This is general linear group. And of course, it is a manifold because this actually turns out to be open set in the set of all matrices, which is n square. Maybe I should write it nicely. R n square. So this is the set of all matrices, n by n. And then, of course, any open set of the Euclidean space is a manifold. So that's clearly it is true. Yes, so another way to describe it is just simply, maybe just remember that this condition can be replaced. This is so just simply determinant of a non-zero. So this can replace the invertibility condition. So similarly, one can also define another group. In such a case, this will be the group of all complex matrices, invertible complex matrices. So let me write it down. This is the set of all A from Cn to Cn. So this is a complex linear map. And determinant, in this case, take complex determinant of A. Of A is also non-zero. Complex of is non-zero. So those are examples. So as this is a manifold here of the dimension n square, you can also figure it out that the next one, number 5, general linear group, complex linear group is also a manifold, because that set is here also a submanifold. Okay, so let's go to the next one, 5, 6, and in this case we can put another example, 6 example. It will be the set of all S, call this one S, a special group, and this will be just simply the set of all A belonging to G, L, and R, and determinant of A is equal to 1. So that's another example of a Lie group. And 7, you can do the same thing with the complex. So let's put complex. And that will be the set of all A belonging to the G, L, and C. And in this case, you take the complex determinant of A, and again is equal to 1. again is equal to 1. So those are the examples, our first examples, but maybe we should concentrate our attention on these, let's say, Lie groups, which will be playing role in the studying of equations with symmetries, namely compact Lie groups. So I'm very interested, put it clearly, we are interested in particular in compact Lie groups. So let's underline, and this is exactly the type of the Lie groups that we will consider of our interest. So let's continue our examples, and notice that all the groups from 1 to 7 are not compact, so they are not compact. These groups are not compact. So those groups are not compact. So in order to give examples of compact Lie groups, let's begin with the first group, which will be called the Zn. This is the group of cyclic group, and we will consider this to be given by the, let's say, roots of identity. So you take Zn is equal to 1, and solving this equation gives you n roots which form a group with respect to the multiplication. So in such a case, we will be considering this to be a multiplicative group with the multiplication given by the multiplication of complex numbers. And this is our cycle group, cyclic of order n. So that's our example 9. Let's go to example 8. Now there's example 9. So maybe let's indicate clearly what it is. So in such a case, because this is a Z, so I can also list all the elements of this group. So this is square, and let's write it down. This is n minus 1. And in such a case, what is gamma? Gamma in our case is a root of identity. So this is I divided by 2 pi divided by n. So you can illustrate, you can visualize the Zn group. Let me make a picture on the complex plane. So in such a case, let's take a circle and then find the roots of identity. So z to the power n is equal to 1. So that's the obvious solution, and then you create a polygon, regular polygon, and with n vertices, and these vertices, first one, that's our gamma, this one is gamma squared, that one is gamma cubed, and this will be gamma n minus 1. So those are the roots of identity that will be considered to be the group Zn. So let's go to the next example. So that's a compact group. Any finite group, maybe make a little observation. Any finite group G is a Lie group. Since we understand that a Lie group is a manifold, so it makes sense to talk about the dimension. You can say like this, of dimension 0. So this is dimensions of this group. So any finite. We will give more examples of the groups that will be of particular interest. Just simply, we will be using these examples in our in our applications, we'll consider them as a kind of a beginning groups for developing all kinds of the concepts, and we'll be illustrating this concept using these particular groups. So let's go to the number 9, and this will be, let's call it S1. So this is S1. So this is just one-dimensional sphere. So this is the set of all. This is set of all complex numbers such that the modulus of z is equal to 1. So that's also compactly grouped as a space. As a space, it is a circle. So this is a circle, and clearly compact. And as with multiplication, also is given by the multiplication by complex numbers. So it's compact. So clearly compact. Let's go to the number 10, and in general we have actually On, which is called the orthogonal group, On. So this is the set of all linear maps or linear matrices of n by n, such that we can have here that A and the transpose is exactly equal to identity. So this will be the set of so-called group, the group of orthogonal matrices. This is the group of orthogonal matrices. And similarly, you can do the same thing. It means you can introduce the group of the so-called unitary matrices. So in this case, those are the complex matrices. And in this case, again, A, and I put here A star, gives you identity. So since A star is a little different than in the case of orthogonal group, so first you take the transpose matrix and then you conjugate, you put conjugation on all the elements, on all the entries in this matrix, on all the entries in this matrix. So this is called the unitary group. Unitary group. Group of unitary matrices. Group of unitary matrices. So let's go a little further. Let's introduce a couple of more. So this will be 11. So our example here is also a special orthogonal group. In such a case, it will be just simply the set of all A orthogonal matrices such that determinant of A is equal to 1. This determinant is equal to 1. And the same we have here US, S, UN. This is the set of all matrices belonging to UN, such that the determinant complex of A is equal to 1. Of course, you can easily verify that the condition, this condition here implies that for the orthogonal matrix, so you have here determinant actually of A must be equal plus minus 1 in this case. And here this condition also implies that the complex of determinant of A must be also equal to 1 in absolute value. But here you just take it like 1, and that's called a special term. So all these groups are the compactly groups, and we will spend time on listing some of the other particular properties of these groups later. And let me point out that there is a kind of a relations between these groups. So notice that the group that S1 can be identified with SO2. With SO2. Indeed, any matrix, if you take any matrix that belongs to SO2, this matrix is actually a rotation, so it can be represented as a rotation, so this will be cosine theta, and this will be equal to sine theta, it's minus, this is sine theta, and this one is equal cosine theta, this is sine theta. So that definitely can be identified, so later, so let's write it down, with the complex number, so which we can call it, we can just simply use here the complex representation of the number ei theta. So that's the complex number that can be identified with this matrix A. Of course, it belongs to S1. So in such a way, we have a nice identification of 2 by 2 matrices with the rotations. So this is from SO2 with the rotations of the complex plane rotations, because this rotation simply means that the map, that means A, acts on the complex number, will be equal, by the definition, it will be just simply equal the product. So this will be the product of ei theta complex multiplication by this z. So this is basically how this identification is meant. So maybe let us also indicate in such a case, since Zn is a subset of S1, so in such a case we can also represent the elements of Zn as matrices, so it will be just written simply that this is equal cosine, this is equal of the matrices, and I put here like this, cosine k theta 0 minus sine k theta 0 sine k theta 0 cosine k theta 0, where k is equal to 0, 1 to n minus 1, and theta 0 is 2 pi divided by n. So this is basically this identification. This is basically this identification. And maybe it's also convenient, so as you see, we can identify it with SO2 is equal to S1, so that's the identification we have here. So what about O2? O2 can be identified with SO2, so let's say it can be written SO2, so those are all the and put it like this, SO2 kappa, all the matrices. So what is kappa? So we know what is SO2, so what is SO2 times kappa? That means you take the matrices, so put it like this, SO2 is equal to the set of all matrices such in O2 such that determinant of A is equal to 1. So kappa can be written as the matrix which gives you determinant minus 1, so notice that determinant of kappa is equal to minus 1. Therefore, any matrix can be written in O2, any matrix in O2 can be written as and that's clearly, this is clearly like that. So any matrix can be written as a rotation. That means from SO2, or reflection from SO2 times kappa. SO2 times kappa. So let me explain why this is actually reflection. So notice that kappa actually is is an operator that for complex number z, it gives you nothing else than z bar. Indeed, you take here 1 minus, did I do something wrong? Yes, 1 minus 1, 0, 0, this is your kappa. Let me go here. Where is my kappa? Rather plus, and this is minus. So let's correct it. So this kappa is exactly 1 here, and this is minus 1 here. Sorry. So this, in this case, is nothing else. So this is a conjugation, complex conjugation. It acts, so kappa is a linear map that goes from the complex numbers to complex numbers, and kappa of z gives you the conjugated number. So in certain way, if you look at the operator of the rotation, then you can immediately notice that if you take kappa and if you multiply it first by the complex numbers like that, then this will give you exactly the results, that this will be ei theta z, and you take the conjugation of it, and you will be getting that this is equal e minus I theta, and that one is simply z bar, and the other one is nothing else than e minus 1 I theta, and this will be kappa of z. And that implies that, therefore, maybe just write it in black, in the group O2, we have that the kappa e theta is actually equal to e to the minus I theta kappa. So these elements anti-commute in this particular way. So rotations do not commute with kappa. The rotations are actually, after under application of kappa, gives you the inverse rotation. So that's the this is exactly what's happening here. So therefore, if you now we have that if you take square of it, k I theta, put here square, you will be getting k I theta k e I theta, which is equal to, okay, so this will be equal e minus I theta k e I theta, and since k and k gives you identity, so this is equal minus I theta, and this is times e I theta, and this gives you 1 again. So yes, indeed, this is self-invertible, so that means it is as it acts on the plane, it is exactly reflection. To be more precise, we can even describe it clearly. So let's show what kind of the reflection it is. You can easily verify. So if you have here, let's say this, I put here like this, a circle. No, not nice. Better. And now let's take element here. This is element e I theta. This is element e I theta. You can verify that if I take so this angle is theta, so I put here half of it, maybe take a blue one. Okay, so this one is theta, and that one is theta over 2. So now you can notice that if I take the element EI theta k and apply it to the vectors from z, so apply it on z, I will be getting exactly the same vector. And that means simply that the operator simply preserves this line and it takes the points which are on the opposite side, switches them to the antipodal, sorry, not this, yes, to the antipodal point with respect to this point. Yeah. Is it? No. That way. So one more time. So this is a reflection. So it just takes to, this goes to that point. Yes. Yeah. Reflection. So let's check it. So if I take the point here, so I take the point EI theta kappa, and that point is nothing else than kappa, and I put here x and times EI theta over 2. So what I will be getting? We will be getting EI theta. Here we are getting conjugation, so this will be x and this will be EI minus theta over 2. So now you simplify it and you will be getting this is equal to I theta over 2. So basically, if this is my vector z, so that's exactly the vector z. Similarly, you can check the other properties. So yes, indeed, this is the reflection. This is the reflection. So so while we are talking about this, because we want to introduce the notion of the dihedral group, and this group is related to the symmetries of the regular n-gon. So what we will do, we will just simply define the regular n-gon on the plane to be in such a position that 1 is basically one of the vertices. So we have here the circle, unit circle, and we inscribe in this unit circle a regular n-gon. So this will be, let's say like that, maybe 8. So we have here n-gon. And here we have the vectors. This is vector gamma, this will be by vector gamma square, the next one will be by vector gamma 3, and eventually we will come here to gamma n minus 1, sorry, minus 2, and this will be gamma n minus 1. So we have this n-gon given here, and we are looking for all the, so we put it like this, dn will be equal to the set of all orthogonal matrices belonging to O2, such that the matrices preserve this n-gon. So if I denote the vertices, so what do I have here? I have here the vertices of this n-gon. So that means put it like this, Pn. So this is set of the vertices of this gon. So there will be 1 gamma, and this will be gamma n minus 1. So of course, in such a case, A applied on this set Pn must be equal to A, and that's not difficult to figure it out, that in this case we have exactly the, as a symmetry is the group Zn, which will be that one. So you can put it like this. This will be actually a Zn. If you use the identification O2 is equal to S. O2 is equal to SO2 union SO2 kappa, so it will be exactly the Zn kappa. So the dihedral group is basically composed of this particular union. So composed. So here clearly these are the rotations, and here we have reflections. So we have here reflections. So this dihedral group here. We can say, in particular, we can think about it are the following groups. So we call that dihedral group. Okay, let's say like this. We have D1, which will be just simply 1 and kappa. We have here D2. So here we have only 1 and minus 1 and kappa and minus kappa. So those are the simplest dihedral groups. And then we have here D3, which will be 1, and this will be gamma, this will be gamma squared, and this is kappa, and this is gamma kappa, gamma squared kappa, and here gamma is equal to EI 2 pi divided by 3, and maybe D4. In this case we have the Z4, which is 1I minus 1 minus I, and then we have kappa, and this will be I kappa, and this is minus kappa, minus I kappa, minus I kappa. So those are the elements. So here, of course, those are the rotations. Sorry. Those are the rotations, and these are reflections. So these are the reflections. So let's move and maybe let me recall the notion of the so-called symmetric group. So the next example is a symmetric group. Symmetric group Sn, which is the, so this group is the permutation group of n elements. So that means, in simply you can think about this as the set of all bijections. So you can say this is the set of all bijection pi or sigma. Here's pi permutation, so of the set of 1, 2 to n. So you take this set and you map it on itself. So this is 1, 2 to n, such that pi is a bijection. So of course, if you take the set and you use here Sn composition of these bijections, so this will be easily a finite group. This is a finite group of n factorial elements. So this is group of n factorial elements. So it is clearly, let's say, if you think about, there are some special permutations. So maybe let me point out, so we have so-called the transpositions. So put it like this: pi belongs to Sn is a transposition. So if this pi can be represented as follows, it takes, you have, for example, 1, 2, and then blah blah blah, then you have here A, two numbers B, so suppose here A is smaller than B, and then it goes to N, then you can write it down that this is 1, 2, and again A, and this will be B, and this is N. So your bijection is mapping 1 to 1, 2 to 2, but it switches, it makes a one switch. Here it switches A with B, and all other numbers are mapped on themselves. So in such a case, this is transposition, and we can write that this is AB. So it switches A and B. One can easily notice put it clearly. One can easily, that's a basic algebra course. Notice that any permutation can be written as a composition of transpositions. That means simply any permutation P can be written like you have 1 transposition B1, and then you take A2, and this will be B2, etc. So this will be written AM, BM. So if you look at this one, you just simply apply it to the set like this. You start from the right and say like that, what happened to it? So here, this means simply that this is transposition that changes AM to BM. And the next one will be changing. So you start from that end and you go to the beginning. Why? Because usually, let's say, the function, like the composition of the function means that what stands on the right is applied first. So that basically is the statement. And maybe also look that we have also a special kind of the, for example, special kind of the let's say permutations. Let's call the cycle an M cycle. So we have here M cycle. So it's a permutation pi, which we actually denoted using this notation. So A1, then we have here A2, A1, then we have A2, and then we have A3, and then this one is AM. So how it goes? So it simply goes like that. If you have here these numbers, so put it like this. You have here 1, this is your A1, this one is your A2, this one is A3, and last one is AM, and the last one is N. So this permutation pi in this case is just again, so this is 3 dots, something else in between, 3 dots, and then you have here A1, A2, A3, this is AM, and this is N. So what do we have here? That A1 is mapped to A2. So that means A1 goes to A2. A2 goes to A3. And that one goes to the next one, and the last one goes back to A1. So it is a cycle. It is nicer to just denote it like that. So you have here A1, it's moved to A2. And A2 is moved to A3. And so on. Eventually you arrive to the last one, and the last one is moved back. The last one is moved back to A1. So that's why we call it cycle. So this, of course, in such a way, this will be denoted by that symbol. So notice, for example, just for the let's say practicing, that A1, A2, AN can be written, for example, as the composition of the transpositions. So look what I have here. I have here A2, and this is A3, and this will be m minus 1, a, and m. So if you apply it to a1, so you're getting a1 moves to a2, and then a2 moves to a3, and then everything, and am moves to am1, and am1 moves to am2, and moves back to a1. So that's this decomposition. So of course we have also additional notions of so-called odd and even permutation. Even permutation is given by the let's say like this. So what is this? This is pi belonging to Sn is even if it can be represented as a composition of even number of transpositions. So we have this notion. So of course, in the same way we can say odd permutation. So that means pi belongs to Sn, and that means is odd if it is a composition of odd number of permutations. Transpositions. So using our previous example, one can easily notice that this permutation a1, a2, am, it is odd, is a odd if m is even, and even if m is odd. So we have it. So one of the properties of the cycles is, maybe put it like this, any element pi belonging to Sn can be written as a product, as a composition of disjoint cycles. What does it mean, disjoint cycles? That means there is no repetition of these numbers in the cycle. So for example, these cycles are disjoint, those are disjoint, and these cycles are not disjoint, because here we have 3 appearing in both. So this is not, those are not disjoint, So you can see that in a certain way every permutation can be represented as a product of disjoint cycles, and that's great. Notice that in such a case these cycles here commute. Yeah. Okay, so now one more notation, so add, so by an in Sn we denote the subgroup of all even permutations which is called alternating group. Of an elements. So this is the alternating group. Maybe kind of exercise, so I put here like a remark. Every finite group can be identified with a subgroup of, let's say, symmetric group Sn. Did I say it? We call it symmetric groups. I think I said it. Symmetric group Sn. Yes, is the group of Sn. So this is kind of a statement can be also kind of easily proved, but we are not doing it. This is not the purpose of this lecture. Maybe we give an example. We have that Dn can be identified with the subgroup of Sn. So again, let's go back to our picture. Maybe let's make a new picture. And let's consider this polygon. And polygon, and then what do I have here? Okay, start with circle. Then we have the polygon. The polygon is regular. This is number 1 standing here. So what if I do the following? So just remove this number 1 and just simply say, I call this vertical 1, because this is my vertical of this polygon, and this is my first vertical. I call this one 2, I call this one 3, so this one will be n minus 1, and that one will be n. So in such a case, I would like to know what happens when I apply any of these elements, put it like this, g belonging to dn, so which is in this case just rotations or reflections. So g basically will move these vertical vertices around. So in certain way we obtain that g permutes vertices of this polygon Pn. We call it Pn before, of the polygon Pn. Maybe Pn vertices. So that means, in particular, if I have here the rotation, the ei theta 0, so what was the theta 0 was equal to pi divided by n. So this actually can be identified with the rotation that takes 1 and moves to the 2. And the vertical 2 goes, vertex 2 goes to the number 3, and so on, and the n minus 1 goes to n. So this is a cycle. So the rotation goes to the cycle. So in this case, for example, in this case of the 6 elements, so we have here like that, so we have here ei theta, in our case, will correspond to 1 goes to 2, goes to 3, goes to 4, goes to 5. So notice what will be I, so that's your gamma. So what will be the gamma square? So gamma square, in our case, it will be 1 goes to 3, 3 goes to 5, 5 goes to 2, and 2 goes to 4. So this will be another cycle. This is another cycle. And what will be the cycle gamma to the power 3? So in this case, you just apply next one more time. So that means, in this case, we'll be getting here that 1 goes to 2, goes to 3, goes to 4. So this will be 1 goes to minus 1. What happens to, what happens to 2? 2 goes to, so 1 goes to, so not minus 1, so goes to the 4. This is number 4. 4. And what happens to 2? So you can see 1, 2, 3. 2 goes to 5. And 3 goes to 5. Sorry. This is 4. Yeah. No. Sorry. 5. 1, 2, 3, 4, 5, 6. Very good. So 2 goes to 5. 3 goes to 6. Yes. This is how it goes. So this will be that one. And then you can continue. And what happens to kappa? So kappa is just simply conjugation. So in such a case, kappa gives you the following. So 1 is met nowhere. So but 2 has to go to n. And 3 has to go to n minus 1, and so on. So in the case of this d6 that is here, this will be just simply 2 goes to 6, 3 goes to 5, just simply 2. These two disjoint transposition. So this is clearly a reflection. This is clearly a reflection. So basically this is the example, and as you see, you can use all kinds of the representations of the groups as a permutation groups, as matrix groups, and we will talk about these particular forms later when we will be dealing with concrete examples. So for a moment, I do not want to create too much notation, so just simply let's stay with what we have and let's introduce a couple of new notions. So notions that are going to be kind of important. So remember, so if we have here, so just remember suppose here, for example, that we have here XD is a metric space. It can be very topological space, house of topological space. And but here we can say matrix space, especially since every Lie group that we'll be dealing with actually is a compact manifold, and every compact manifold is metrizable, so that's enough. So suppose here this is a metric space. And suppose here that we will denote by B of X, this will be this is the sigma algebra of the so-called, and we call them Borel sets. So what are those Borel sets? So namely, that means this is the smallest sigma algebra of sets, of subsets in X containing all open sets. So all open sets. So in our case, if I talk about the Lie group, so for compact Lie groups, so we assume that we'll be dealing now with the compact Lie groups. So for a compact Lie group, the set, if I write it down, B, and I put here, okay, Lie group G, we will write this is Borel sets, and I put here G. That means this is the smallest sigma algebra generated by the all open sets in G. So what does it mean, a measure space? So if you have here sigma algebra, then a measure space, then one can consider a measure space. One can consider measure space, and this will be like that. I put here my G, and I create the Borel sets, and the measure I denoted by mu. So this is basically a function that takes, that we usually write it down like just this is mu, and this maps the Borel sets, and it maps, I put here 0, possibly infinity in general, so I don't exclude it, but in our case, it will be finite. It will be finite, so because group is compact, so let's say it's finite. And now, of course, we are interested in a specific different groups. Notice that if A belongs to the BG, then what does it mean? That this is a subset of G, and we also have two types of different subsets. I can write it G of A is also a subset of G, and I can also write A, and I multiply it from the left, is also a set of G. So you just multiply. So what is this? This one is the set of all Gx, such that X belongs to A, and that one is equal to maybe I don't need to put here minus. I don't want to put here minus. I just put here AG is belonging to G, so just write it down like that. So this is Gx such that X belongs to A, and that one will be just simply Xg such that X belongs to A. So in general, you are expecting, let's say if you have, this is clearly by the continuity of the operations of the multiplication, you can easily notice, even here you can replace it by minus ones, of course, you can replace it. So you can also notice that here we have that this set, you can write, okay, maybe even like that, A minus 1, this is sequence of X minus 1 such that X belongs to A. So those are also Borel sets. So that means all of them are Borel sets. Then you have here GA, AG, and this is A to the power minus 1, like it is defined here. All belongs to the Borel sets on G. So the question is very simple. The question is very simple. What happens to these measures? In general, the measure that does not satisfy this property, okay, in general, you don't have this property that the shifted, we call it like the shifted or rotated, or okay, let's say shifted or set A may have a different measure. So such a case, when you have actually the properties like that we have here, like this mu, and this is g of a is equal mu of a. So we will say that the measure is left invariant. The measure is left invariant. And if in addition you have also mu ag is equal to mu a, then this measure is right invariant. It's right invariant. So we have here one of the very famous theorems which says that such measure that is left and right invariant always exists on the compact Lie group and is unique. And we can say up to the normalization, so if we assume in addition that the measure of the whole group is equal to 1, so such a measure always exists, and it is called the Haar measure. So Haar measure. So let's, since this is a kind of important information for us, so let us formulate as a theorem. So let G be a compact Lie group then there exists a unique sigma additive measure mu. No, we just simply write unique measure. That means it's on the sigma algebra. So unique measure mu that goes from the Borel sets of G to 0, 1, 0, 1, called the Haar measure. On G, satisfying so let's put here A, that it's invariant, so we have here G of A is equal mu of A. B, mu of AG is also equal to mu of A. C, that mu of G is equal to 1, and maybe that D, that mu of A minus 1 is also equal to mu of A. In addition, we also have here additional two properties, which maybe I added here in additional A. I put it like this, that mu of A is equal to supremum over mu K, such that K is contained in A, K is compact. And F, that mu of A can also be written as infimum, and this will be mu of U, and this means A is contained in U and U is open. So this is for all A belonging to B, G, and I think we used also G belonging to G. So this is basically let's say the statement. So this is how measure exists, and now let's say like this. So if you have a measure space, since then, okay, once we have a measure space, and this is our measure space, so I have G, this is my Lie group, this is Borel sets, and this is Haar measure here. Mu is Haar measure. I can say the Haar measure because it's unique. Can also we have the Lebesgue integral. We can introduce the Lebesgue integral. So we can introduce the notion of mu measurable functions and that's exactly, and maybe put it like this, f that goes from G to R, and define the so-called Haar integral. So this is called Haar integral. Haar integral. Haar integral. So that's exactly the integral that is associated with this Haar measure. So in such a case, we will write simply that we have here integral, and this one is equal to G f d mu, and now we write it that this will be the same using, if you want to use the variables, to put it like this, f g, and this will be d mu of g. So this is our notation, and this integral is just a simply integral like it was for every kind. Yeah. So what do we have here? So the integral satisfies the usual properties of integral, of an integral associated with the measure, and in addition we have that, put it like this, property 1, this will be that integral over g of f, and I put here like this, h minus 1, and this will be g d mu g is equal to integral over g this is g over g, and this will be f g h d mu g, and that one is actually equal to f g d mu g. So it's invariant. So maybe just call it P property. P. invariant property. I put both of them here. Okay, of course, the idea that I put here minus is just a convention, but you can notice that this is not essential. This has no particularly any importance here. Not importance here. So, of course, maybe this is a good moment. Maybe this is a good moment to stop. We stop here. And we'll continue with the topic next time. We'll review more properties of compact Lie groups, and we'll introduce more notations, more symbols. So I think it's a good idea to stop here.